You open the application for the first time, and the interface already feels foreign. The layout has changed since the last update. A button that used to sit in one place now sits in another. A feature that did not exist a few months ago is suddenly treated as essential, as if you should have already known it was there. You send the command. Nothing moves. For a second, you assume it's the system. Then you realize it isn't. You know what you want the tool to do. You can see the options in front of you. The information is right there on the screen. It just takes longer to turn into action than it should. The same thing happens the next week, with a different tool, doing the opposite of what worked the week before. And somewhere underneath the frustration is a quieter question nobody asks out loud. Why does this keep happening? Every time something new arrives. Most people explain this to themselves the same way. Learn faster. Pay closer attention. Stop being lazy about it. The explanation feels reasonable because it puts the problem inside your willpower, somewhere you can control it. But the early signs of this rarely show up as willpower failing. They show up as small frictions that are easy to dismiss. A new system takes more attempts to understand than the last one did. Switching between two unfamiliar tools feels more draining than it used to. Mental fatigue arrives earlier in the day, after less effort than before. Recovery afterward stretches from minutes into something closer to hours. None of this looks like decline from the outside. You still show up. You still get the work done. You still sound like yourself in conversation. The unfamiliar tool gets returned to later, on a quieter day, and somehow still takes longer than it should to feel natural. Even though nothing about your intelligence has changed. Even though you could explain the concept clearly to someone else right now. A similar quiet shift is documented in the earliest stages of mild cognitive impairment. People who remain fully independent, who manage their lives competently, who simply notice that new information no longer settles into place the way it once did. Not the past. The past is fine. It's the next thing, the unfamiliar thing that resists. That distinction is the one most people miss. Intelligence and adaptability are not the same biological process. A person can carry decades of expertise and excellent judgment while quietly becoming slower at the one thing that determines whether any of it stays useful: updating. The visible problem looks like artificial intelligence moving too fast. The question underneath it is whether the brain itself is still able to keep up. Adaptation is not a choice. Adaptation feels like a decision. It is treated as a decision constantly, in performance reviews, in self-help language, in the quiet self-blame that follows a frustrating hour with new software. The brain does not experience it that way. Every time you absorb something unfamiliar, neurons inside the cortex have to physically change how they communicate with each other. The prefrontal cortex, sitting behind the forehead, has to build a new working model while holding back the old one that keeps trying to interfere. The hippocampus, buried deep in the temporal lobe, has to take a raw, disorganized experience and stabilize it into something the rest of the brain can use later. Regions scattered across the cortex have to link language, memory, and attention into a single coherent picture, and white matter pathways, the wiring between all of it, have to carry the signal fast enough for any of this to happen in real time. None of these systems act alone, and none of them act instantly. A single unfamiliar command, one button, one new menu, can require all four working in sequence before it becomes something you no longer have to think about. None of that is optional. None of it can be skipped by trying harder. Adaptation is not psychological, it is structural, and structural change has a cost.
If you're fascinated by documentaries like this, subscribe to Pathology of Fear. New medical documentaries every week.
The cost of change. The mechanism behind that cost is called synaptic plasticity, the capacity of a connection between two neurons to get stronger or weaker, depending on how it's used. One of its most important tools is long-term potentiation. When a circuit fires repeatedly, the connection becomes more efficient at carrying that signal the next time. What took deliberate effort the first 10 times begins requiring less the 11th, the 12th, the 20th, until eventually it runs almost on its own. The change happens at a precise location, the dendritic spine, a tiny protrusion where one neuron receives a signal from another. Strong enough, repeated enough activity lets calcium into the receiving neuron through specialized channels. And that influx sets off a cascade that inserts more receptors into the synapse and can physically widen the spine itself, leaving behind a thicker, more efficient channel for the next signal. None of that finishes instantly. The chemical cascade unfolds over minutes. The structural part, the new receptors, the widened spine, is often not fully locked in until hours later, frequently during sleep. This is what's happening, invisibly, the first week with a new platform. Every menu you search for, every mistake you make, is the brain in the middle of physically rebuilding itself around the task. That rebuilding is expensive. New proteins have to be synthesized. Receptors have to be repositioned. Existing assumptions sometimes have to be partially dismantled before the new ones can take their place. Learning has never been free. It has always been paid for in biological currency. And for most of a person's life, the body pays that bill without complaint. When the machinery slows, the decline rarely arrives as a single moment. There is no morning where the ability to learn simply stops. Instead, synapses gradually become less responsive to the exact signals that used to trigger remodeling so easily. The machinery is still there. It just no longer fires with the same readiness. Long-term potentiation is one of the first systems to feel this. The same repeated activation that once reshaped a connection quickly now produces a smaller change. The threshold required to trigger that calcium cascade rises. The same intensity of repetition that used to reliably push a synapse past the point of change now falls short more often and has to be repeated more times before it succeeds. What used to take 10 repetitions starts requiring 20. What used to stabilize in days starts requiring weeks. Nothing about this looks like failure in daily life. Existing knowledge holds. Old skills, built on networks that were optimized years ago, keep functioning exactly as they always have. The weakness only shows up at the edge, in the unfamiliar, in the new. An experienced professional can understand a concept completely and still need far more exposure than expected before the related skill becomes usable. The knowledge was never the problem. A senior employee may grasp exactly what a new AI workflow is supposed to do within minutes of the explanation and still take weeks longer than a junior colleague to actually operate it without hesitation. Not from lack of comprehension, but from a synapse that simply requires more passes before the same circuit locks into place. The lesson lands. The update doesn't finish. The wires between the rooms. Synapses are not the only structures involved. Somewhere underneath all of it, an entire communication network has to keep functioning, and that network is built out of myelin. Myelin insulates the long fibers connecting distant brain regions, allowing signals to travel between them quickly enough for coordinated thought to happen at all. The hippocampus encoding something new has to talk to the prefrontal cortex evaluating it, which has to talk to association regions, linking it to everything you already know. None of that coordination happens instantly. It happens through wiring that itself has to adapt. The cells responsible for that insulation, oligodendrocytes, wrap a fatty sheath around each fiber in segments, leaving small gaps where the electrical signal regenerates as it travels. Thicker insulation, placed more precisely along the gaps, means the signal regenerates faster and loses less strength along the way. The precursor cells that build this insulation respond directly to neural activity. They adjust how much myelin gets laid down around circuits depending on how often those circuits are actually used, which means the wiring itself is shaped by repetition, not fixed at birth. With repeated use, the brain can reinforce frequently active pathways, shaving fractions of a second off the time it takes signals to travel. This is part of why expertise feels different from struggling, not just more knowledge, but a faster, more efficient route for that knowledge to move through. That optimization slows with age. Brain imaging studies that track these pathways directly, most often using a technique that measures water movement through tissue called diffusion tensor imaging. consistently find measurable changes in white matter integrity with age, even in people showing no obvious symptoms. The insulation doesn't disappear. It simply becomes less responsive to the demand for new, faster routes, and existing routes lose a small amount of their precision. The task is familiar. The efficiency underneath it is quietly gone. And because well-worn pathways stay intact, this kind of decline hides easily behind routines that never change, only revealing itself the moment something genuinely new has to be built from scratch. The gatekeeper of novelty. At the center of all this sits the hippocampus, not simply a memory bank, but the structure that decides what counts as new and worth integrating in the first place. Every unfamiliar interface, every unfamiliar workflow has to pass through it before it can become part of what you know. Without that gateway functioning well, new information stays fragmented, present, but never fully assembled into something usable. Part of what supports this function is the brain's limited capacity to generate new neurons in adulthood, a process concentrated in a narrow strip of hippocampal tissue called the dentate gyrus. The cells generated there appear to specialize in something researchers call pattern separation, the ability to keep two similar experiences, two similar interfaces, two similar updates from collapsing into a single blurred memory. With enough new cells coming online, a new platform stays distinct from the last one it resembles. Without enough, the two start to blend. That generation of new cells appears to decline with age. The exact extent is still debated among researchers, but the consequence observed clinically is consistent. Novel information increasingly has to compete with older, more established patterns instead of settling in cleanly beside them, and similar but different inputs are more likely to get treated as the same input, even when they aren't. This pattern appears in far more severe form in conditions like mild cognitive impairment and Alzheimer's disease, where long-established memories often remain intact, sometimes remarkably so, long after the ability to encode anything new has already started to fail. A person can recall a wedding from 40 years ago in vivid detail, while being unable to remember being told the same instruction 20 minutes earlier. The past survives. The future stops arriving correctly. The information arrives. The update never fully completes. It is the same gatekeeper, simply operating at different speeds in every brain that ages. The compounding effect. None of these systems decline in isolation. They lean on each other, which means a small weakness in one becomes a larger weakness in the next. Attention determines what gets encoded in the first place. Top-down attention control, the brain's ability to deliberately direct focus rather than simply react to whatever is loudest, relies on the same prefrontal networks already stretched thin by adaptation demands elsewhere. When that control weakens even slightly, less information makes it through to the hippocampus with any real clarity. Weaker encoding produces a thinner memory trace. A thinner trace gives the rest of the brain less material to build a stable network around. Slower network building means the whole adaptation cycle takes longer to finish, which leaves less attention available for whatever comes next. Each link in that chain is small enough to ignore on its own. Together, they surface as something people describe simply as exhaustion. A cognitively demanding day that used to end in tiredness, now ending in something closer to depletion, with recovery stretching further into the evening, sometimes into the next day. The fatigue is real. It is just downstream of something quieter than fatigue. The cost of switching. A slower gatekeeper changes something else too. The ability to let go of a strategy once it stops working. Cognitive flexibility looks from the outside like a personality trait. Someone is called open-minded or stubborn, adaptable or resistant. Underneath, it involves something larger than a single brain region. Large-scale control networks spanning the prefrontal and parietal cortex that have to reconfigure their pattern of connectivity depending on what the moment demands. One configuration supports familiar, automatic behavior. A different configuration has to assemble itself when an old strategy needs to be set aside for a new one. That reassembly is itself a form of plasticity, and brain imaging research shows it happening more slowly and less completely in older brains, even on simple laboratory tasks with no real stakes attached. Underneath that, It is the prefrontal cortex deciding, second by second, whether an existing approach should be kept or abandoned, suppressing one pattern while strengthening another. Both halves of that decision require plasticity. As plasticity declines, the switching itself becomes more expensive, and the brain begins favoring whatever pathway already exists, simply because it costs less to use. This is frequently mistaken for unwillingness. Someone keeps reaching for the old method, even after admitting the new one is better. It looks like resistance. It is closer to economics, the nervous system choosing the cheaper option, the one that doesn't require fresh construction. The solution still works. The environment around it no longer does. A world that never waits. For nearly all of human history, the environment changed slowly enough that this cost barely mattered. A craftsman could rely on techniques learned in youth for an entire career. A farmer could pass down methods with little fear they'd be obsolete by the next generation. The Industrial Revolution sped that up. But even then, a major shift might unfold across decades, leaving room for adaptation to fully stabilize before the next one arrived. A person might encounter 2 or 3 major transformations across an entire working life, each one separated by enough years for the relevant networks to finish remodeling. The information age compressed the timeline further, into years rather than decades. Artificial intelligence has compressed it again, not as a single new tool, but as something that accelerates the creation of new tools continuously, across nearly every field at once. A platform learned this year may be substantially different within months. A skill built last quarter may already need revising. Some of the tools involved did not exist in their current form even a year ago, and may not exist in that form a year from now. The machine updates immediately. The brain does not. Software can be pushed out overnight to millions of systems at once. Synaptic remodeling, myelin remodeling, hippocampal encoding, none of that can be rushed past its own biological timeline, no matter how urgently the environment demands it. Earlier shifts in technology also tended to affect one task, one industry, at a time. Artificial intelligence touches communication, research, creative work, education, and decision-making simultaneously, which means several adaptation cycles now have to run at once inside the same limited biological budget, rather than arriving one at a time with room to finish in between. The gap that won't close. When change keeps arriving before the last adaptation has finished, the result is a specific kind of strain. Not an absence of intelligence, but a widening gap between what the environment now requires and what the brain has had time to build. At first, the gap stays small enough to ignore. Existing knowledge still supports the basics. Familiar routines still work. The strain becomes visible only when several unfamiliar systems arrive close together. When one half-finished adaptation has to share resources with the next one before it's even stabilized. Attention gets divided. Encoding gets shallower. What should have become one integrated skill instead settles as several disconnected fragments. A person who can operate 3 separate parts of a new workflow individually, but who has never had the uninterrupted stretch of repetition needed to fuse them into one fluent sequence. People in this state often describe themselves as capable but overwhelmed, understanding things individually while struggling to hold the whole picture together. That description is closer to a biological bottleneck than a discipline problem. The environment updates. The brain is still mid-update, and every additional demand that arrives in that gap doesn't reset the process. It just gets added to the backlog. Environmental mismatch. Eventually, the math stops resembling effort and starts resembling debt. Learning one unfamiliar system already consumes attention, encoding capacity, and the slow structural work of synaptic remodeling. If a second system arrives before the first has finished stabilizing, the brain doesn't pause the first task to focus on the second. It runs both at once, each one quietly borrowing resources the other one still needs. A third arrival doesn't reset that count. It adds to it. And the systems already learned don't stay still either. Most get revised again before the brain has finished optimizing for the version that came before. The target isn't only multiplying, it's moving. This is the point where falling behind stops being a temporary lag and starts behaving like debt that accrues interest. An unfinished adaptation cycle doesn't sit quietly until there's time to come back to it. It keeps drawing on the same limited pool of attention and metabolic resources that every new demand also needs. The backlog doesn't shrink during a slow week. It compounds during a busy one. For most of human history, this didn't need a name, because the gap between environmental change and biological adaptation rarely grew wide enough to notice. The two speeds were close enough to treat as one. They no longer are. The environment isn't occasionally outrunning the brain's capacity to update. It has become, in an ongoing and structural sense, simply faster than the biology responsible for keeping pace with it. Not for one disruptive season, but as a standing condition. The debt accrues. The payment never quite clears. That is the deeper shift sitting underneath the everyday feeling of being behind. It isn't a deficit waiting for a quieter weekend to repay. It is the new relationship between a nervous system built for a slower world and an environment that has stopped waiting for it. When it becomes visible, eventually the gap stops being something only the person themselves notices. It shows up first as avoidance, someone quietly defaulting to the older method even after acknowledging the newer one is better. Observers usually read this as stubbornness. It is more often a nervous system protecting itself, gravitating toward the pathway that costs less to use, the one already built rather than the one still under construction. It shows up next as hesitation, a slight pulling back from unfamiliar situations that didn't used to feel risky. Not a loss of curiosity exactly, more a quiet awareness that experimenting now carries a cognitive price it didn't used to carry, and it shows up in recovery time. A demanding stretch of learning that once resolved itself overnight now leaves a residue that lingers into the next day, sometimes the day after that. It can also show up as a quiet erosion of confidence, not because ability has actually dropped, but because the felt effort of staying current keeps climbing. And effort is one of the few signals the brain trusts when judging its own competence. None of these are character flaws being revealed. They are a biological cost curve, finally steep enough to be felt. The limits of repair. None of this is fixed in place. Neuroplasticity exists on a spectrum, not a switch. Sleep consolidates the day's learning, completing structural changes at the synapse that began hours earlier. Cardiovascular exercise increases blood flow to the hippocampus and raises levels of a protein called brain-derived neurotrophic factor, which directly supports the growth and survival of new connections. Continued mental engagement helps preserve the very networks responsible for absorbing anything new, a quality researchers often describe as cognitive reserve. These factors can meaningfully slow the decline. They cannot remove the underlying biology. Cellular repair becomes less efficient with age regardless of habit. Inflammatory activity rises gradually. Mitochondrial performance changes, reducing the energy available for the costly work of remodeling. The brain can compensate for a long time, rerouting around weaker areas, leaning on networks built decades earlier. But compensation is not unlimited. In Alzheimer's disease, that compensation eventually becomes overwhelmed entirely, and the gap between old knowledge and new learning becomes impossible to ignore. Normal aging follows the same direction at a far gentler pace, but it is the same direction. The system improves with care. The ceiling stays exactly where it was. What was always there. None of the biology in this story began with artificial intelligence. Synaptic plasticity, hippocampal encoding, myelin remodeling, cognitive flexibility, all of it has been quietly aging inside every human brain since long before the first computer existed. For most of history, the environment never moved fast enough to reveal where the edges of that system were. The limitation stayed hidden, simply because nothing demanded enough speed to expose it. A slower aging synapse and a faster aging one looked identical for an entire career, because neither was ever asked to prove the difference. Artificial intelligence did not create this vulnerability, it revealed it. The world used to change slowly enough for the brain to keep pace with it. The modern world is the first to consistently move faster than that. not as an exception, but as the new default. Artificial intelligence will almost certainly keep advancing. That part of the question is barely in dispute anymore. The quieter question, the one that gets far less attention, is whether the nervous system carrying each of us through that advance can keep evolving alongside it. Not in theory, not as a species across centuries, but inside one aging brain, on one ordinary Tuesday, the next time something unfamiliar arrives before the last thing has finished settling in. Underneath the frustration of a confusing new interface, underneath the quiet embarrassment of needing the same instructions twice, sits the same unremarkable biological fact that has always been true. The brain only stays current by physically rebuilding itself, a little at a time, every single day. Most days, that rebuilding finishes quietly, completely, without anyone noticing it happened at all. Some days, it doesn't quite finish before the next demand arrives. The interface keeps changing, the command keeps getting sent. Most of the time, somewhere beneath conscious awareness, the brain finishes the work before you ever think to ask whether it would. It has been doing this, without applause, for the entire length of your life.
Pathology of Fear is a medical documentary series presenting clinically documented neurologic and pathological mechanisms for educational analysis.